Alright, volatility ordered set heap. I encountered it during my master's thesis, so I'm interested in revisiting what it was all about one more time. Let's see. So it is not a standard.
A volatility ordered set heap isn't a standard universally recognized data structure in computer science literature by that exact name. However, the term strongly suggests a composite data structure designed to manage unique elements, ordered by a calculated volatility metric, using a heap-like mechanism for efficient retrieval of the most, or least, volatile items. Let's break down the components, and then conceptualize how such a structure would work, along with its practical applications and a code example.
So here is a sample run for the code for VOSH. So creating the heap first, then we have adding items, stock A 5.2, this is the volatility score, stock B with the volatility score 1.8, then stock C volatility score 7.5, stock D with 3.1. So picking least volatile, for instance here. So these are the cores. So let's see the output. Adding item, stock A, stock B, stock C, stock D, then picking least volatile, stock B with volatility 1.8, then stock C, and so on and so. So I have already mentioned that I have encountered during my master's this data structure. While doing my master's thesis, it was in a relevant work. So there are some real-world applications, of course. Here we are first going to listen about real-time anomaly detection in cybersecurity.
In cybersecurity, imagine a vast network with thousands of servers, user accounts, and endpoints. Traditional monitoring can be overwhelmed by the sheer volume of data. What volatility represents? For a user account, volatility could be the frequency of failed login attempts from unusual geographical locations, or access to sensitive files. For a server, it might be an unexpected spike in CPU usage, network traffic, or error logs. How the heap helps. Each network entity, server, user, device, is an item in the heap. Their volatility score is continuously updated based on real-time security events. The heap ensures that security analysts can immediately pull the top-end most volatile entities. This allows rapid identification of potential cyber attacks, compromised accounts, or failing infrastructure, enabling proactive intervention rather than reactive cleanup. 2. Dynamic resource allocation in cloud computing. In a large cloud environment, virtual machines, VMs, and containers constantly fluctuate in their resource demands: CPU, memory, I/O. Efficient allocation is critical to performance and cost. What volatility represents? For a VM or container, volatility could be the rate of change in the last minute, the frequency of memory allocation requests, or the variance in its network throughput. How the heap helps. Each VM/container is an item. Its volatility score dictates its priority. A scheduler can use a volatility-ordered heap to quickly identify the most unstable or rapidly changing workloads. This allows the system to intelligently reallocate resources, migrate workloads, or even provision new capacity before performance bottlenecks occur, ensuring optimal resource utilization and service quality. 3. Algorithmic trading and market surveillance. Financial markets are a prime example of environments with constant, rapid change. Traders need to react instantly to shifts. What volatility represents? For a stock or financial instrument, volatility is a statistical measure of its price fluctuations over a period. It could be calculated from standard deviation of returns, volume spikes, or sudden news impact. How the heap helps. Each tradable asset is an item. The heap is ordered by their current market volatility. Algorithmic trading systems can query the heap to immediately find the top-end most volatile assets. This enables automated trading strategies to capitalize on sudden price movements, or for human traders to focus their attention on the most dynamic parts of the market, identifying opportunities or managing risk more effectively. 4. Real-time news trend analysis and alerting. News platforms and social media aggregators need to identify breaking news and trending topics rapidly to provide timely updates. What volatility?
I'm going to ask another question. How can it help in developing contextual embedding text data. So, trying to develop
This is an excellent and insightful question. While the volatility ordered set heap isn't directly involved in its contextual embedding over time or across different contexts, here's how a volatility ordered set heap can help in developing contextual embeddings for text data. 1. Understanding volatility for contextual embeddings. For text data, volatility tied to contextual embeddings can refer to semantic drift, how much the meaning, and thus its embedding vector, of a word or phrase changes over time or when used in new, unexpected contexts. Topical emergence/shift, how rapidly a new topic or concept, represented by a cluster of related terms embeddings, is gaining prominence or changing its core associated terms. Contextual variance, how much a term's embedding varies when observed across a diverse set of current documents, indicating its polysemy or use in new ways. Salience/importance, how frequently or significantly a term appears in the most relevant or recently active parts of a text corpus. 2. How the volatility ordered set heap fits in. The heap would store unique words, phrases, or entities as its items. Their volatility score would be a computed metric, reflecting their semantic change or contextual activity. Conceptual flow. 1. Initial embedding corpus. Start with a large text corpus and a pre-trained contextual embedding model, e.g., Bert, Roberta, etc. 2. Item extraction and initial volatility. Extract key terms, phrases, or named entities from incoming text streams, e.g., daily news, social media feeds. For each unique item, generate its initial contextual embedding. Assign an initial, perhaps low, volatility score. Add these items to the volatility ordered set heap. 3. Continuous monitoring and volatility calculation. As new text data arrives, reevaluate the contextual embeddings for the terms within it. Calculate volatility score. Example metrics. Cosine similarity with historical average. Maintain a running average embedding for each term. The volatility score could be 1 minus text cosine underscore similarity, text current underscore embedding, text historical underscore average underscore embedding. A lower cosine similarity means higher volatility. Clustering distance. For a term, calculate the distance of its new embedding from the centroid of its historical embedding cluster. Larger distances indicate higher volatility. Frequency in new topic clusters. If a term consistently appears in newly formed or rapidly growing topic clusters, identified via topic modeling on embeddings, its volatility increases. 4. Heap update. For each monitored item, update its volatility score in the heap. As discussed, this might involve adding a new entry and effectively invalidating the old one. 5. Extraction and action. Periodically, e.g., every hour, daily, extract the top and most volatile items from the heap. 3. Real-world scenarios in contextual embedding development. Here's how this would apply. A. Dynamic vocabulary and semantic shift detection. Scenario. You have a search engine or recommendation system for a fast-evolving domain, e.g., AI, cryptocurrency, pop culture. New slang emerges, or existing terms acquire new meanings. Moon in crypto, ghosting in relationships. How it helps. The heap identifies words or phrases whose contextual embeddings are drifting significantly. For example, if AI starts appearing frequently with terms like generative art and large language models, rather than its historical associations with robotics and automation, its volatility score will spike. Benefit. This alerts you to semantic drift. You can then prioritize retraining your contextual embedding model specifically on text containing these volatile terms to capture their new meanings. Automatically update your search index with the refined understanding of these terms. Flag ambiguous terms for human review or disambiguation in search results. B. Real-time trend and event detection. Scenario. A news aggregator wants to identify breaking stories or emerging topics faster than traditional keyword matching. How it helps. The heap monitors entities, people, organizations, locations, and their associated terms. If a specific entity's mentions suddenly appear in a high volume of new, unrelated contextual embeddings, indicating a sudden event or a new discussion trend, its volatility score will jump. Benefit. Allows for the immediate detection of emerging trends or breaking events based on the semantic context rather than just keyword frequency. This can trigger automated alerts, curate dynamic news feeds, or inform content creation strategies. C. Improving information retrieval and relevance ranking. Scenario. A document search system needs to return the most currently relevant documents, where relevance might be tied to how a term's meaning is currently understood in the user's query context. How it helps. When a user queries for a term, the system can check its volatility. If a term is highly volatile, e.g. cloud in a tech context, but it's now shifting towards climate change in recent articles, the system can be biased to prioritize documents where cloud is used in its currently most volatile, i.e. new/emerging context. Benefit. Provides more dynamic and contextually accurate search results. It moves beyond static keyword matching to understanding evolving meanings. D. Adaptive Natural Language Understanding, NLU models. Scenario. Chatbots or virtual assistants need to understand user intent accurately, even as language evolves. How it helps. The heap can monitor common phrases or intents. If the contextual embedding of a phrase like, I'm sick, starts showing high volatility, shifting from illness to cool/awesome, the NLU model can be flagged for update. Benefit. Enables more resilient and adaptive NLU models that can keep pace with linguistic evolution and new expressions, reducing misunderstanding and improving user experience. Conclusion. A volatility ordered set heap provides a powerful framework for dynamically identifying and prioritizing semantic changes within text data, driven by contextual embeddings. It acts as an early warning system for evolving language, emerging topics, and shifts in meaning. This enables developers to proactively manage, refine, and adapt their text processing systems, ensuring they remain relevant and accurate in a constantly changing linguistic landscape.